Okay, let's get started. Hello, everybody. Welcome to the talk on the JVMs.compare. This is a talk where we're going to compare benchmark performance across different JDK, JVM combinations. Quick introduction. My name is Chandra. Don's here with me. He's going to introduce himself. We're both Java champions. We're two of the three representatives for the JCP Executive Committee representing Bank of New York Mellon. We're ardent bloggers and tweeters. I'm a director at Bank of New York Mellon. I've been working in the financial sector for a while and with Java for much longer. I am one of the leaders for the largest Java user group in North America called New York Java SIG. If you visit New York, please do keep us in mind. And I'm a creator of the Java Kata's GitHub repository that is quickly gaining popularity. So thank you if you've already starred. Otherwise, thank you for your stars that are going to come tonight. With that, I'm going to hand it over to Don to introduce himself.
All right, thank you, Chandra. Welcome, everybody. Hopefully you're enjoying Code 1 this year. We got like a full set of talks in front of you today. So yeah, a little bit about myself. As Chandra said, we both work at BNY Mellon. We're on the JCP Executive Committee. I've been working in finance now, financial services for around 18 years. Been programming in Java since 1997. I was a member of the JSR 335 expert group, so JSR standing for Java Specification Request. That's how we changed the Java language. JSR 335, for those that don't know, that was the JSR that got lambdas and streams into Java 8, which was released back in March 2014. Quite an honor to be on that and to kind of see all the work that went into all the great features in Java 8. I'm also the creator of the Eclipse Collections library. Was formerly known as GS Collections, originally open sourced in 2012 from Goldman Sachs. I've been working on Eclipse Collections, GS Collections for the last 15 years. I've written more benchmarks than I care to even recall. Benchmarking is, and you'll get to hear some of this today, a not so great way to spend your time, and you will spend a lot of it when you start benchmarking things and looking at things and tweaking things. I saw a tweet recently where somebody said, you can add like 1,000 lines of code in an hour, right? You can maybe like delete 10 lines of code over a day. Doing benchmarking, you may change one flag over a week, right? As you're running things. So you'll get to see that. And there was a picture on the first slide I'm going to talk a little bit about.
Remember the slide.
Yes. I'll talk about this in a bit. So, but yeah, so that's a bit about me. And I guess we can get to the next slide. So, just a context. So our Twitter handles are at the bottom. Like Chandra said, we both actively tweet and blog. If you can't get a good picture there, it's on my back. Shameless self-promotion. Anyways, we'll continue. Today, the things that we're actually going to go over. There's a set of benchmarks that I actually wrote 2 years ago. They're somewhat a naive set of benchmarks, right? So I haven't spent a lot of time trying to tune the benchmarks at all. I originally wrote them for a kata that sits out in the BNY Mellon code katas in GitHub. And basically, the benchmarks that are out there were meant to be a way for other folks to come in and say, like, hey, I want to learn JMH, and maybe I want to write my own benchmarks. So they sat out there as a kind of like a teaser for like, hey, this is a place where you can learn how to actually just use JMH and start playing with your own benchmarks. So the benchmarks that are out there and that we're going to actually be covering today, we're doing some benchmarks against a primitive list and also list of integer. The original benchmarks were written so we were comparing basically Eclipse Collections. Once again, Eclipse Collections creator, shameless advertising. So we're comparing Eclipse Collections as well as JDK collections. Now the interesting thing, the benchmarking that we did for this talk, I didn't really care about the differences between the two collections frameworks. I care about the differences that we were hoping maybe to see between different JVMs, and that's what you're all here for. So we have primitive list, also a boxed version of it for JDK, and then we have a list of persons. We wanted a more interesting object, not just a simple wrapper object or primitive. We wanted something that actually had a little bit more weight to it, and literally it has weight. Person class actually has a name, an age, a weight, and a height. Right, so more, slightly bigger object, and we wanted to see what the effects of that were. So that's a little bit about, what we'll be talking about with the benchmarks.
Great. So on that note, thank you, Don. What we are attempting to do here is to compare 8 different JDK JVM combinations. You have Oracle JDK version 8, which is what is the trendsetter for us. Most of the JDKs we use are 8-based, and we will talk about this, except for one which we had to use for reference, and we will cover why. So we use Oracle JDK 8. the latest version that is available. We use Graal VM Enterprise Edition 19.2.0 that just came out 3 weeks ago. Community Edition as well, which came out in the same time the Enterprise came out. And then we also use Adopt OpenJDK, which is quite popular and notable across the community. We use version 8 of that. Adopt OpenJDK can run at 2 flavors. It can use the hotspot, and it can also use what's called an OpenJ9 virtual machine. So there is a simple flag that you could set, or you could download a different binary in order to get a different output. So you can either do hotspot with Adopt OpenJDK or Adopt OpenJDK with OpenJ9. So we downloaded both those binaries. And then in the mix, we threw in OpenJDK 11, and there is a good reason and intent for us to do this because of number 7. Number 7 is where OpenJDK now has an embedded Graal inside it. It's a community edition of Graal, but it is just to prove that Graal itself is embeddable, that they have included a Graal virtual machine inside of OpenJDK, and you can enable it. It also includes a Graal VMCI compiler. We'll talk about that. And likewise, on the opposite flip side, Graal VM Enterprise Edition also contains a JDK hotspot. So we can turn on a flag there, or turn off a flag rather, and get the C2 or the hotspot compiler to be used instead. So those are the different combinations of JDK JVMs we are testing out. Again, it's the same set of benchmarks. Like Don pointed out earlier, it really doesn't matter what these benchmarks are or how deep we went into them. We're just comparing the exact same benchmarks across different JDKs and JVMs. So on that note, Don?
Yeah, so the first benchmark that we have is just a simple filter. And basically and we basically do, you know, a little bit have 2 different sizes of lists, but basically we want to filter a list based on the even numbers in them. And we're going to go with a very large list and then a smaller list. Then we do simple operation, a reduce operation. We do sum, right? So we basically take the entire list and just sum it. Then the final operation that we actually test is a transform. So we're taking the source list, actually applying some function to it. In this case, we're applying, you know, times 2, right? We're going to multiply every int times 2 and then come up with a new list of those ints. And there's 5 different benchmarks in each of these, you know, I guess high-level benchmarks. So we'll be testing, for instance, like Eclipse collections for primitives, Eclipse collections boxed, JDK boxed, Eclipse collections with streams. So a bunch of different combinations of stuff are tested in here. So on the object operations, because we have a more interesting object, we can actually do more tests. So the first thing, we actually first wanted to do filter again. And this is really testing that, okay, well, we have a bigger object. I want to see what the impacts of having that bigger object in collections are, applying a filter against it. And we're filtering all persons, you know, between the height of 80 and 150 inches. Then we do filter and grouping, right? So we're filtering the persons less than 150 inches tall and then grouping them by their age. Then we apply a calculation, you know, using in-summary statistics. So for those that aren't familiar, in-summary statistics is a class that came out in JDK 8. Includes, you know, basically it keeps a running tally of the min, max, count, sum, and then calculate the average for an int set of values. So we do that by age for all people. And then we do a combined summary statistics. So we're basically doing 3 passes against all the people. We're doing their ages, their heights, and their weights. Min, max, average, count, sum, min, max, sum, count, and average. Sorry, thank you.
Okay, great, thank you. So yes, these are really tall people, in case you didn't notice. So in order to run these, we were talking about this earlier, there are a few JDK flags that we had to use. First, caveat statement. We just used every single JDK out of the box. We did not tweak any flags. We did not try to achieve any performance gains out of any JDK. We simply downloaded the JDK, and in 2 instances, we set a flag to either use another virtual machine or not. Those are the only flags we've used. This caveat is important because we're trying to be very unbiased and neutral in how we are presenting this. Some graphs may indicate that certain JDKs don't show you good output, but we are trying to justify why that is the case. We have not tweaked any flags anywhere. The first flag we used was in OpenJDK to run the Graal compiler. You unlock experimental options, and the second flag is not really necessary anymore, but we just included it. But the third flag that says plus use JVM CI compiler is what hints to the OpenJDK 11 that it should use a Graal compiler instead. That is flag number 1 we used. The other flag that we used is in the GraalVM Enterprise Edition, we provided it a hint to actually use the hotspot or the C2 compiler by saying minus use JVM CI compiler. Again, the first one is not really necessary, but we just included it just in case. Just remember that there's a minus and not a plus if you're ever trying to experiment with this. Great. On that, Don?
Okay, so this is the hardware that we used for testing the large collections and really to validate what's going on in some parallel tests, right? So shout out to my wife. I have to give her a plug on this slide because I bought this machine 6 years ago so I could actually help the open source community by making sure we can make Eclipse collections as fast as possible for serial and parallel operation. I said that's really important, more important than sending our kids to college or to buying a car. So shout out to her. This is important. 6 years later, you're all going to appreciate this, right? We'll get a large round of applause for like me having spent money on this thing. Thank you, thank you, thank you. All right, good. I can go home now after this talk. So, but anyway, so it's a Mac Pro. My kids call it the trash can because it looks like a trash can. It blows a lot of hot air when we run these tests. And actually, that was on the first slide, you saw those green columns. If you see a lot of green, it means that we're running parallel tests, and basically the 12 cores and 24 threads against those cores are just heating up my office, right? I'm waiting to get my electricity bill at the end of this month to see what the extra impact was, and I'll have to be like, okay, you all clapped, so I can say it was worth the electricity cost as well. So anyways, it's a 12-core machine. It once again has 24 threads. It's got 64 gigs of RAM, 1 terabyte of solid state, and pretty much I use this machine for nothing else other than benchmarking, right? Well, browsing. I actually do most of my development on my laptop. But it is great when we need to do benchmarking, which is what we need to do here. So great to have it around.
And we had very little time to do that.
Yes, and once again, remember I said you change one flag, you run, then 7 days later you have something that happened. There were like 5 days of my life spent heating up my office for this particular talk. So.
And not to mention, we ran this on the latest versions of Graal that just came out very recently, so we waited, and we reran the test with the latest, so you get to see more accurate results. And the machine does get really hot. I was there. I've seen it.
It blows the air up. I don't know if you've ever seen the Mac Pro trash can. It's amazing, the architecture. Like, this fan just blows up heat into the air. It's amazing.
All right, so this is the other machine we used, this little monster. And this was where we used the smaller benchmark seeders, which is 1,000 size collections. This is the machine you already seen how it looks like. It's a 2-core machine, and it was able to survive with a 1,000 seeded benchmark run. Just in terms of math, right? This was probably the last, slide that we want to talk about, and then we go into the graphs because we want to get hands-on. We have 7 benchmark classes in total. There are 3 for your int list, and there are 4 for the person. Don already covered those. And we have 8 JDK JVM combinations. We listed them out for you. We ran it twice, once with a large size, once with a small size. Both times we looked for throughput, mode.throughput, what we use for our benchmarks, with a 1 million size and with a 1,000 size. That was the beast, which was number 1, and the second one was the little monster. Ran those. There are 39 total benchmarks across these 7 classes. The math is done there. And then since we executed it twice, it was 4,368 benchmark runs. Just a quick note for those of you who are not very familiar with benchmarks, throughput benchmarks are easy to read as long as you remember that the higher it shows up on a graph, the better it is. Throughput indicates the number of operations you're performing over a period of time. So always look for spikes upward. Spikes downward indicate that throughput is not good. Therefore, your benchmark is revealing that something is not right there. Okay? Great. On that note, here is the benchmark source. It's available on GitHub. You can download it. And then our benchmark visualization tool, which was amazing for us, is the JMH.
Yeah, this is like a tribute to open source developers everywhere. Get that address. If you're ever going to run JMH benchmarks, you need to know about the JMH More Than I.O. Site, because JMH, which is a great tool by itself, if you're going to actually write any micro benchmarks, that's the thing you should use if you're benchmarking in Java. But at the end of the benchmarks, you get a nice table laid out by JMH. But if you need to actually do any graphs, I've historically had to do that by hand. JMH.more-than-IO, which we discovered for this talk. So this was great because here we're putting a talk together. I learned something new that actually saved me a ton of time on the talk because we're comparing all of these benchmarks. And I was like, I'm going to have a nightmare of like weeks in my office, like trying to get Excel to parse, nice graphs out of this. But JMH more-than-IO actually did it for us, and that's what you're going to see today. So that's a good takeaway for everybody if you do any micro benchmarking.
Awesome tool. Okay. So the first thing we want to do, even before we start showing you the graphs, is how do we read these graphs? It's important to know what we are communicating here so we can have synchronization of ideas. So this is what each graph will look like on our screen. The x-axis is the JDK and JVM that we're using. They're listed numerically 0, 1, 0, 2, 0, 3, and we have an index of what these are, so you can refer back to it very quickly. The y-axis is the throughput. Higher is better, and if it's lower, it indicates that something is wrong. And then the line itself is individual method, the benchmark method that each class contains. So each method execution has a different color. The y-axis is where the throughput is, and the x-axis is individual JDK, JVM combinations.
And pay attention as we go through the slides, because you're going to see the same benchmark twice, one for 1 million, one for 1,000. And what's going to be interesting is watch what happens with the colored lines. It's very important. You're going to see them move, and
they don't stay the same.
Yeah, and it's got to do with basically running parallel and serial tests and understanding, when you run parallel tests and expect to get performance out of parallel, you have to have the right problems for parallel code to actually give you a benefit. You need, a large data size, complex operations, and you need multiple cores, right? And we've got combinations of those things, like because we have the beast, it's got cores, but on the little monster, we don't have a lot of cores, right? And it's got small data size, so.
I should really upgrade.
You can have my beast. I'll tell you the price later.
Okay, so this is our first measurement. So like Don was pointing out, the orange Q up top indicates that this was run against a 1 million size, and you can notice the legend on the right, which indicates what JDK JVMs are used, and they're numerically listed out on the x-axis for you to read. Here, we just want to show you the first measurement. Look at filter EC parallel, which is the orange line up top. It's an indicator of what is going on here. The throughput is very high when it comes to 0.2, which is Graal Enterprise Edition 19.2.0. Once again, just to reiterate, we did not set any flags or tweak or tune any JDKs, so this is an out-of-the-box test, and there could be potential noise when you're showing some graphs. So don't take these at face value. Please do run these benchmarks yourself.
Also recall as well, like the benchmark itself, we're filtering 1 million ints. If that's your use case, maybe this benchmark would be useful to look at, but more likely you've got more interesting use cases than this one. It's one very small use case. So
yeah, the best thing is take cues from our source code, create your own benchmarks, evaluate what you need rather than rely on what content we're showing. We're just providing you information on how we did it because of our use cases. So there you go. Here, the 0.2 Graal EE seems to be very performant, and the rest seem to be almost on the same line, give or take a little bit. So this is a great graph against 1 million. Now notice that this was where filter EC parallel, I guess the purple one out there is filter JDK box parallel are higher throughputs than everything else. So like Don was pointing out earlier, when you're running across a larger size, parallels start showing you benefits. Don, you want to add something to that?
No, I guess all I would add on this, which I talked about before, these benchmarks were written well before we put this talk together, and we used exactly those. And those benchmarks were intended for us to compare Eclipse collections, let's say operations against JDK. We didn't know what to expect when we actually plotted these graphs. This was a surprise for us when we sat down and looked at it for the first time. We had no expectations. We didn't know what to expect. So,
great. Moving on to the next graph. This is a 1K size, as you noticed from the green cube below. And you'll notice that there is a subtle change in the graphs now. Not just which ones executed better. You'll notice that now the serial is higher throughputs than the parallel is, which indicates that it's very obvious after you run the benchmarks that if you don't have a very large volume, don't parallelize. Use more serial. And if you have a lot of volume, you should consider using parallels.
There's something else in this graph as well, is if you see the top line there, that's a primitive collection, right? So you've got no boxing and unboxing effects that are happening when you're actually doing the filtering, right?
Which makes it more efficient in this case. Great. So we covered a collection size of 1 million and 1,000, And this was the filter operation. That was the first operation that we talked about when Don was explaining the different kinds of benchmarks we ran. Next is a sum or a reduction operation. And in this case, you'll again notice that the EC parallel and to a certain extent, the EC primitive have higher performance on some JDKs. And there is a significant dip when you use, let us say, Graal Community Edition in this case. That could be noise. It could be based upon what we were testing. We don't know. We are just showing you the results as we see them.
Yeah, something interesting on this slide as well is if you look, the top line there, with the large hump over on the left is a parallel test. But if you look right below it, the green line, that's serial primitive, right? So what you're kind of seeing here is sum is an extremely fast operation, right? Doing plus on like a primitive is extremely fast. Parallelizing it, and having the extra cost of parallelizing is not going to give you maybe as much benefit as you'd expect, right? We're not seeing like, I'm not seeing a 12 times performance improvement over the primitive version here, right? It's barely, what is it? Maybe like 30, 40%.
Yeah, not much. Okay, now. This was the collection 1 million size run across a reduction operation. We repeat the same thing with a 1,000. And let us see what changes in the graphs here. We notice that when you have a smaller size, primitives obviously are going to perform better. But the parallels sort of start taking a nosedive, which is consistent with what our messaging has been. When you have a small size, maybe you shouldn't be using parallel.
Yes, now just to say as well, like just because you see the parallel lines are very low, it didn't reduce the amount of heat generated in my office, right? So I was still melting an iceberg somewhere, but you're not getting any performance benefit out of it. You're just doing a lot of extra work.
Right, and another thing to add is it would have been awesome if we had more time to separate the serials and parallels into different benchmarks, so they would be much more visible. We had a time problem on our hands in that we were trying to run it with the latest versions of everything, which meant we had to do this right before the conference. So we took a little bit of a shortcut here, which is why some of the parallel lines show very tiny. Okay, moving on. This is the transform operation on primitive lists. We took an int list transform, and it converts something in the int list. It converts the integer into some other integer. And you notice again here that the parallel operations benefit from, show more throughput when you run across a large size. One thing we did notice is here, adopt OpenJDK running OpenJ9 took a nosedive. This may be noise again. So we're not claiming that it is actually slow. It could just be that there is a high error rate on the benchmark run that we ran.
What I'd want to do right away is like run these again and again and again and see that this is consistent, right? And not just some noise.
Yeah, so we ran it twice. Maybe people should run it more often and run it across different sizes or whatever your needs are in order to test what benchmarks work for you. But again, this is what we needed, and we're looking at how we proceed at looking at these JDKs. When we use a smaller size collection, let us say a 1K size collection, we notice that the primitive operations, again, start showing up as more higher throughputs.
But you also see now OpenJ9 is actually doing better than all the rest, right? Whereas it took the nosedive on the previous one, right?
Yeah. So again, everything with a spoonful of salt. Determine what you need based upon the benchmarks you want to run. Run your benchmarks frequently to know that you're making the right decisions. Now, we did all these primitives up to now. We saw which JDKs we were evaluating and how they stood. And now when we come into the object, the larger object size, the first one we're doing is person filter. So we are sort of filtering persons whose heights are within a certain range. And that operation, as you can see, we performed, and the parallels obviously are going to do better than the serial because it is a very large size. And Don, do you want to add something else about this?
I would just say, like, I mean, you're looking at this graph, right? When we switch from the primitive operations to the larger object, operations with the person object, to me, like, this looks like they're almost all equivalent, right? There's not any huge swings in any direction. A neat wavy pattern here, but like, I would say like, there's definitely noise between all of these anyways. So like, they all seem like pretty equivalent here,
So the best inference we can make is when you use more objects, I guess garbage collection kicks in?
Well, there's also potentially cache misses, right? You may actually have to go from level 2, level 1, to main memory to get stuff because it's in the bigger size, right? We've got bigger objects. They're not likely to just all be available directly in a L2 cache or L1 cache.
there you go. But one thing I did notice is the throughput changes. So going back, that is in Ks. Operation is 380 Ks at the top. When we go to person, we are at 360. The sizes are basically the number of operations. I'm sorry, this is the one I want to show you. It goes up to 600. So more operations on person object than on primitive object. So that's something we noticed. It was interesting. So this is the 1K size operations, and you can see that its graph went upward. More throughput started coming in when we started using objects. This could be because there could be some, like Don was pointing out, maybe caching is going on, maybe garbage collection is going on, maybe there is some inlining going on. We don't know. But it's consistent across most JDKs. Of course, there's one hub that Graal EE had, but the rest of them look almost consistent with how they are operating. This is the second operation we were performing. This is a person filter in group operation. We basically took people who were below the height of 150, and we filtered them out, and then we grouped them together by their heights. Yep. That is the operation we performed. So it's more complex. We were evaluating something more closer to business logic, where we are making decisions based upon content we filtered, and then we group them together into buckets. So again, we noticed that when we run against large sizes, parallel operations clearly win. Across most JVMs, there's a sudden dip in, let us say, OpenJDK 11 using the Graal C2. It could be noise. Or maybe it isn't. Maybe it is because it is a very old version of Graal CE, right? Or maybe it is just the fact that it is consistently dipping because maybe it's a hint you should not be using that. Instead, use Graal CE or Graal EE instead, right? These are things for you to evaluate. Once again, running it multiple times is how you will know if this is what you should be evaluating or not. Don?
Nothing to add here.
Nothing to add here. This one was interesting. This is for the 1K run. This performed lesser number of operations than other 1K runs for some interesting reasons. I still haven't figured them out. But what you can still see is most JVMs seem to be sort of going in the same pattern. But what we did notice was Graal had a very high performance peak on this one. Graal EE did. And once again, you will notice that serial operations perform better when you have smaller sizes. So
yeah, I guess a slight raised performance too, like with OpenJDK 11, right? So
there you go. Okay. This was the summary statistics. So we collected the height of, I think we collected the ages of people, the ages of the person and object, and we created summary statistics around that. And this operation is a mathematical operation on an object. And what we did notice is graphs were very consistent, except for Graal Community Edition and OpenJDK 11 Graal, which is again a community edition, took a little bit of a dip.
And again, this could have been noise. I'd want to run it, probably a few more times.
Well, it could also be primitives. Maybe Graal CE is not, I guess, suited to handle primitives as well as it handles objects. We don't know. But it was a very interesting graph. We're studying these, we're analyzing this, and we'll also show you the source code of how we got there, so you have background about why these graphs are important to us. With a smaller size graph, we noticed that the in-summary statistics were more or less similar to what the largest size was. It is operations. I guess performing more operations in parallel is somewhat better when you have large sizes, but I could not positively make that assessment just by these two graphs. They look similar. We noticed that Graal Community Edition, for some odd reason, did very well here. But in the prior chart, the Community Edition was the one that did not do well. So was that noise? Was that Graal optimizing somehow because of differences in operations? We don't know. Then this is combined summary statistics. This is the last of our statistics that we used. This is where we not only took their ages, but also their heights and their weights, and did summary statistics across all three. Ages were integers, heights and weights were doubles. So we had two double summary statistics and a single int summary statistic created as an object, so way more complex in operation, 3 different reductions, and 1 object creation as a part of our benchmarking. The graphs are very interesting and consistent here. You notice that there is a dip when you get to Graal Community Edition. You notice that when you use adopt OpenJDK with hotspot, you get a sudden spike. When OpenJ9 gives you a lower benchmark throughput. And then OpenJDK 11 hotspot seems to do very well here. that's a mystery. Maybe they've made some improvements, performance changes in OpenJDK 11 that are adding to this. You'll notice that adopt OpenJDK 8 and OpenJDK 11 are almost giving you the same amounts of throughputs. Very interesting to note that. So once again, what are you using? What is your need will drive what benchmarks you should look at. So create your benchmarks according to your needs, and you will know, you'll be able to make better decisions. Yeah.
The two reds are rather similar. Which is the higher red?
Oh, that's a great question.
Okay, so
I think
I'll answer it two ways first. We can't control the colors, that's number one. But this one, the parallels are the one that show up at top.
Sorry?
The parallels are the operations that show up at top.
yeah, so it's the combined JDK statistics parallel. Yeah.
Okay, and the last one we have is when we use person combined summary statistics across a smaller size. This is for day-to-day operations. Maybe you just have 1,000 size container and you're trying to run all these complex operations on an object. Once again, we notice some significant trends when it comes to Graal CE and when it comes to adopt OpenJDK, OpenJ9. Now, this is by no means a critique of adopt OpenJDK or a bias towards any JDK or VM. This is what we ran out of the box. I keep reiterating this because there could be other benefits you get from using other JDKs. You may get better startup times. You may tweak flags and get better performance than what we show. But this is what a normal developer, when they download a JDK without tweaking, can run and expect using these benchmarks.
Yeah.
That's what we're trying to communicate.
I think one of the things we learned out of this as well is, and I think it's a good thing, right? There's actually a project called Renaissance Dev that is basically, going to be collecting up benchmarks from the open source community, and be used to actually benchmark different vendors. Because again, doing this is an expensive, both in time and electricity and hardware as well, like set of things to be doing, right? So developers doing this on a daily basis, I wouldn't recommend it unless you've got a lot of time on your hands and you're really curious and bored.
Or you live in a very cold place.
Yeah, but it is nice to know that there's a place where we can actually maybe start to contribute some of our own benchmarks, and maybe you want to contribute some benchmarks to it as well, and actually open it up and actually have it vetted then by different JVM vendors. We didn't vet any of our benchmarks here with the JVM vendors. We took the ones that we had, and that's what we ran with, right? But you can actually see a lot of maybe improvements that can be made to individual benchmarks, and working with others is a good way to do that. One of the things that we did want to actually see if we could do is see if we can actually demo the JMH More Than I/O site. Yes, go ahead.
Before you go off that chart, you can put that chart back.
Absolutely.
This seems to be sort of grossly misleading because you're showing you ran 1,000 items through, you're getting 90,000 throughput, which means that the total time of these runs is minuscule.
It is.
And so therefore comparing them is hard to discern any meaning because there's so much noise in there that this graph is meaningless. So this is really sort of a bit dishonest to present this as performance data.
One of us is dishonest. I'm presenting as it ran, right? I took a small.
He's running 1,000 data items through here, and he's showing a throughput of 90,000 per second, which means this thing ran for hundreds of milliseconds. There's so much other noise in the system that could dwarf these numbers. There's no idea what these numbers mean. The other one, at least, is a bit more meaningful. You run 1 million through, and you're showing hundreds of operations per second.
Yeah, and I think this is where this is once again where you can actually have the benchmarks themselves vetted. I'm going to admit like this particular benchmark is somewhat naive, but the thing is like even running on a small operation, yeah, you can have a lot more noise and there might be a lot more impact, and the graph may not be as meaningful. But this is where we're like, we kind of rely on the expert engineers like working on JMH to actually help us, build something that actually can report, at least something that's somewhat meaningful in it. So this isn't me taking system time, current time milliseconds before and after, right? I'm leveraging JMH to actually do it, so.
The fact that you measure throughput that is 90,000 per second over a collection set of 1K doesn't mean that you have noise on this page. It's not related. I'm sorry, I don't see it.
Well, you know what? Why don't we talk after the talk? If we can actually demo the site. Do we have time? Or?
Absolutely. I believe we have time, but definitely would like to extend this conversation to after the talk. So this is a site we use, jmh.morethan.io, in case you didn't take a screenshot earlier. And let's try a live demo of comparing a few results. Typically, what I'd like to propose that we do is compare, let us say, Oracle JDK 8, OpenJDK 11, and maybe Graal EE against the 1 million. So let's take the most complex of all the person combined summary statistics, and we take Oracle JDK 8 and Graal EE, for instance. Let's compare these two. So right away, you notice that there is a pentagram that shows you where the most error rates are. It shows you which benchmarks did better, which didn't, and it allows you to compare individual or download JSONs for each, and we'll go through. Yes. That's a good point, thank you. Let me first full screen it. Visible? Okay. What we find better to do is also do the comparisons across the different operations between two JDK JVMs to see where some operations do better and others don't, and we can make an evaluation based upon that, which JDK JVM we could use. So the benefit of using the site, and kudos to jmh.morethan.io, you get a lot of things for free. You get to see the JSON output of the benchmarks themselves. You get to see both, you get to compare, and you also get to see a summary statistics of what changed or where the error rates were higher or which one was doing better in terms of throughput.
Yeah, I think the great thing about it as well is it's open source, so you can actually take contributions to it as well. So I'm not sure what the contribution agreement is with the site. The site itself is pretty good, but might be improvements that could actually be made. And since it's open source, I'm gonna contribute to it if people are interested. So.
Great.
But yeah, I mean, once again, doing this by hand just from the raw output would be painful. So this saved us a tremendous amount of time, right? Otherwise, I'd probably still be in my office, like tweaking with Excel to get graphs that I could show here.
This is one thing that I usually like comparing, Graal EE versus OpenJDK 11. Graal EE is based on a JDK 8 compiler for now, and we've heard that a new version of Graal is coming out soon that's going to support JDK 11. So we're looking forward to that. Okay, here's a quick comparison of Graal EE versus OpenJDK 11. And you notice that the OpenJDK 11 does do better in some places because they've made significant improvements. Let's take a quick look at what changed. You notice that serial operations and parallel operations are somewhat doing better in OpenJDK 11, which is awesome. But this is one measurement across two different, JDK JVM combinations. Great. I think I'm done with the portion of demoing this.
Yeah, so I think we can actually take questions. We have what? I think 5 minutes. Yeah. Okay, so the question is, were any of the Graal tests using a native image? And the answer is no. We did not use native image at all.
Yes. So no tweaking of any kind. It was just an out-of-the-box binary download. Set it up with Maven and run across as tool chains in Maven that both compile the code in the JDK JVM combination and then run the benchmarks in the same.
Yeah. So one of the things too, I guess, like as I was saying, I've written tons and tons of benchmarks to tune Eclipse collections, but I was looking for specific things, and we don't run them all the time. They're all checked into the Eclipse collections repo. If we wanted to run them, it might take like 10 to 20 days to actually run them all in a single pass, right? But with now knowing that there's this thing called Renaissance Dev out there and a place to potentially contribute benchmarks to, it's something that I find interesting as an open source developer working on Eclipse collections framework that maybe we'll actually contribute some of our benchmarks and have them tested and vetted. So I don't have to sit in my office running it against the beast and taking my electric bill either. Use some other cloud provided hardware. So.
Renaissance.dev is cool. I think we should have included a link to that as well.
Yeah.
But renaissance.dev should be easy to remember.
You want to bring it up? Is it? Yeah, we found out about this, at the tail end of our, talk that this is out there. So, as we were preparing, and I think like there's the benchmarks here as well that people contribute under different licenses.
Right there.
This one? Or?
Yep. Unless it opens in a new tab. It's still loading.
Yeah, so that's out there as well. Any other questions? We've got 5 more minutes.
5 minutes.
Yes.
Yeah, so the question is, does the JMH visualizer also show other data from the benchmark? Yes, it does. So, correct. So there are 3 modes of its operation that we found, and they're very useful. You can take a single benchmark JSON file, dump it, and you get all that information. When you put 2, it compares one against the other. And when you put 3 or more, it produces the graphs that we were looking at, the line graphs we were looking at. So it has done all 3. The only thing is currently it does not allow us to tweak colors or label the X and Y axis ourselves, which is why we had to go through the pain of explaining why, there's what the X axis and what the Y axis is.
And once again, it's open source, so that's maybe something if somebody really wants could be contributed. So.
But that aside, it's actually an amazing tool. It lets us build these graphs out very quickly, get information from that. So very grateful to have that tool around.
Other questions?
Was
yes.
throughput always directly relational to time, directly proportional to time, or was ever a case where the throughput was high, but the performance was low? Like, were they always correlated with each other?
So
was one of the JVMs like doing something clever to run a problem faster?
We didn't actually look into the JVM code itself and talk to any of the JVM engineers to figure out, like, is there something magical going on here? So,
but there were some visual cues that you could see, obviously, that there are some graphs which consistently kept the same shape when run both with a large or a small data set.
And actually, are there any JVM engineers in the audience? JDK JVM? I mean, the benchmarks are out there. You can take a look at them. If you find anything magical you want to, that your JVM does or doesn't, do to make something faster or slower, we'd love to hear about it. So.
No. So it does warm-up cycles first, and after that it starts calculating based upon the iterations that we provided.
Yeah, and I think. No, and I think we were doing, 10 warm-up and just 10 runs to limit the total amount of time that we actually had to run these on. But yeah, you can specify with JMH, like, how many warm-ups, start up to get any noise out, so. Did we do 2?
2 forks.
Yeah.
That was a great question. Thank you.
Thank you. Other questions? All right, once again, we're going to have the source code is out in the repository if you want to take a look. The benchmark results are out there as well. You can, as Chandra was just doing here before, if you want to play with the JMH more than IO, you can drag our results there and do different comparisons if you want. Thank you everybody for coming today and listening to our talk. So. If you like the talk, hit the green vote button. If you didn't like the talk, hit whatever button you want to. And we'd appreciate feedback as well if you think there's anything we can improve. This is our first time, doing this, type of comparison. Once again, I've done lots of benchmarks to look at the individual slices, but never anything across JVM. So, all right.
Have any of the JDKs been updated since you ran the test?
No.
They would have to be updating very quickly because last week was the runs finished.
Last week, so.
Exactly. Oh, it's faster now. Yeah, so, okay, thank you.
Thank you.